Welcome back to part 2 of Aggregate Planning. In this video, I'm going to go over linear programming and demonstrate a very simple problem. Our aggregate plan model is essentially a very large LP. So we need to know the basics of LP before we can tackle the larger production planning problem. So if you're already familiar with linear programming or LP, then you can skip this video and head to part 3. So how can you actually find the best production plan? We have to solve an aggregate planning problem. So we have to first formulate this problem and actually solve for variables. This is a iterative process. You can do a trial and error. That's one approach. You create a spreadsheet model and just try different numbers and see what you get. I don't recommend this. You could also use what I propose, just linear programming. You can do so on Excel using Excel Solver, or if you're familiar with tools such as MATLAB, which I personally prefer, then this is another way to do it. You could also use nonlinear optimization methods. A lot of times though, for these aggregate plan models for production planning, a linear model using Excel Solver is good enough to tackle most of the problems. In order for us to come up with the best production plan, we have to take all of our relevant information and formulate an LP. Now, LP is a very common optimization method used in many different applications. In operation research, this is one of the most common ways to solve problems. So a basic application, here's an example. Let's say there's a shop called Joe's Vintage Cars, and Joe's business is converting old convertibles into custom cars, and he only produces two types of products. The California Legend model, so these are customized convertibles. Both types require a $12,000 plain convertible, so some old convertible they didn't convert into either a California Legend model. So after Joe makes the conversion, the California model sells for $25,000, and Joe actually has to spend $10,000 in parts to do so. Joe can also create a Legend model and sell it for $30,000. In order to do so, he needs about $14,500 in parts. Joe wants to maximize his profits. That's the objective. So what's the objective function in this scenario? Joe wants to maximize his profits. So then what are the profit margin for each type of vehicle? The profit margin would just be the selling price minus the cost to build for each type of this vehicle. So for the California, each California sells for $25,000. The convertible costs $12,000, and the additional parts is another $10,000. So we have $25,000 minus $12,000 minus $10,000 for a net profit of $3,000. Okay, so that's how much it costs, or that's the profit that Joe gains when he takes a existing convertible and converts it into a California model and sells it. For the Legend model, it sells for $30,000. The old convertible he's taking to convert into Legend costs $12,000, and it requires $14,500 in additional parts. And the net profit here is $3,500 per unit. There are some couple implicit assumptions I'm making here. First assumption is that there's enough demand to actually for people to buy California. So whatever Joe produces, it sells. And another assumption we're making is the labor cost is already embedded in here. So this is excluding the labor, or you can assume that the labor costs are excluded here. Then we have to identify or declare our decision variables. What can Joe actually control here? So the first thing to control is the number of California model to produce and sell, and also the number of Legend model to produce and sell. So we're going to let x1 equal to the number of California produced and sold, and we're going to let x2 equal the number of Legend produced and sold. Then our objective function then is going to be the maximization of $3,000 per unit of California times x1, which is the number of California produced, plus $3,500 per unit for the legend times the actual number of legend produced and sold, x2. We could let this whole expression equal z, then essentially we're maximizing this value z. Okay, so Joe wants to know the best number or the optimal value for x1 and x2 such that it maximizes this value z. Obviously, there are limitations or constraints to this process. Joe can't make infinite number of California models or the legend models. There are constraints here. Joe is limited to the number of cars he can convert. The shop can work no more than 12 cars in a week. There just isn't enough capacity in the shop to work on more than 12 cars in any given week. Labor is limited. Joe has only so many number of employees and employee hours to actually perform the job. So Joe has 7 employees who work 8 hours per day, 5 days a week, and we're assuming here there's no overtime. A California model takes 20 hours to make, so you take the existing car and convert it into California, it takes about 20 worker hours to do so. A legend model takes longer, about 25 hours. So these are my constraints. So now actually take these constraints and turn it into mathematical relationships. Okay, I'm going to first write up here what we already declared. X1 is the number of California models, so I'll just say California, and x2 is the legend model. Okay, so we already declared this on the previous slides. The first constraint we have is the total number of cars worked per week. So we know Joe's shops can't work on infinite number of cars in a given week. There's limitations. So at most, they can work on 12 cars at any given week. So then we know x1 plus x2 cannot exceed 12 cars in a given week. Okay, so whatever combination Joe can decide to work on, all 12 cars being California, or all 12 cars being legend, or some combination of the two. The second constraint is the total number of labor hours. There's only so many labor hours given for this shop. We know there are 7 employees. Each employee works 8 hours per day, and there's 5 working days in a given week. So we multiply this, and the total labor hours available for Joe is 280 hours for any given week. And we know for every California model, it requires 20 hours of labor. Every model of legend requires 25 hours of labor. So the sum of these two labor hours cannot exceed 280 hours. For a lot of these constraints, if you're not sure, one easy way to check whether your constraints are written correctly or not is simply check the units. We know the units for this 20 here I'll just write it like this, 20 hour per, I'll call it unit, which is the unit of car, and then x1 is actually units, right? So these two cancel, you're left with hours. Same argument here, and then we know the units here is hours. So if I were to left, these are actually worker hours, but yeah, essentially the unit here is hours. Now we're actually ready to write out our full LP formulation for this problem. Our objective function is, again, to maximize our profits. And we know for every unit of x1, the profit margin is going to be $3,000. Okay, and then for every x2, the profit margin is $3,500. This is my objective function, such that the constraints are such that the sum of x1 plus x2, this is simply from the previous slide, cannot exceed 12 cars. So the number of cars that Joe works on any given week cannot exceed 12. Second constraint is 20x1 plus 25x2 cannot exceed 280. So these are the labor hours, so worker hours. Every unit of x1, which is a California model, consumes 20 worker hours. Every unit of x2, the legend model, consumes 25 working hours. So total cannot exceed 280 hours. And our final constraint They're non-negativity constraint. X1 and X2 has to be non-negative. So you can't build a negative car, right? So this is a very simple example of LP that we have to take this and apply it to our larger aggregate planning model for this plan. So you'll see that bigger example in the next video. Thank you.